Hello, welcome back to Tall Building class. Today, we will study about seismic load. Firstly, create seismic load by click, load. Lateral load. Static seismic loads. A window will pop out. Today we will study how to fill in all the fields of this panel. First of all, we need to select the corresponding load case. Here, we create a seismic load in the X direction. Select desired standard. Midas Gen provides multiple standards for calculating seismic loads such as International Building Code 2012, which equivalent to American Standard for Minimum Design Loads for Buildings and Other Structures 2010. National Building Code of Canada. Eurocode 8. Indian Standard. Korean Building Code 2009. Chinese Code for Seismic Design of Buildings. In this lecture, the seismic load is calculated according to the American Standard for Minimum Design Loads for Buildings and Other Structures 2010. In practical designs, engineers may encounter different types of standards according to owners. However, you can adapt to another code quickly if one standard is thoroughly understood. Determine site class. According to Guide to the Seismic Load provision of ASCE 7-10, sites is classified based on soil types. Each site class has a pair of coefficient FA and FV that are included in response spectrum calculation. There are 6 classes, A, B, C, D, E, F respectively represent ground conditions from hard rock to soft soil as the following table. Let's take a closer look at each site class. Class F, according to the standard, the site is considered as Class F if any following condition is satisfied. 1. Soils vulnerable to potential failure or collapse under seismic loading, such as liquefiable soils, quick and highly sensitive clays, and collapsible weakly cemented soils. Two peats and, or highly organic clays. The thickness of soil is greater than 3 meters of peat and, or highly organic clay. Three very high plasticity clays. The thickness of soil is greater than 7.6 meters and plastic index is bigger than 75. 4. Very thick soft, medium stiff clays. The thickness of soil is greater than 37 meters and undrained shear strength is smaller than 50 kPa. Class E, for soft clay according to the standard, the site is considered as Class E if it does not satisfy the criteria for Class F, but there is a total thickness of soft clay greater than 3 meters. Soft clay is defined by the following criteria. Class C, D, E. There are 3 methods that can be applied to classified Class C, D, E. 3 methods are: 1. Using shear wave velocity of the top 30 meters. This parameter can be measured by downholes or cross-holes method. 2. Using standard penetration test results of the top 30 meters. Three. Using standard penetration test results for cohesionless layers and undrained shear strength for cohesion layers of the top 30 meters. If the classification outcomes of the standard penetration test and undrained shear strength are different, the final decision should follow the softer soil. Class A, B. Class A and B can only be verified by shear wave velocity. Besides, sites cannot be assigned as Class A or B if there are more than 3 meters of soil between the bottom of foundations and rock surfaces. Conclusion: Class E and F can be determined based on the appearance of weak soils. Class C, D, and E can be classified by 3 methods. Engineer can assign Class D if there is not sufficient data and there is no sign of Class E or F. Class A and B can only be determined by shear wave velocity. The limit values for classification are summarized as follow. Before digging deeper into the problem, we should spend a few minutes to learn about the concept of acceleration response spectrum. The acceleration response spectrum demonstrates the relationship between the peak acceleration and the fundamental period, natural period, of structure. The following figure shows a design acceleration response spectrum. X-axis shows the fundamental period of structures. Y-axis shows the response acceleration of structure under earthquake. From left to right, the fundamental period increases and structure stiffness decreases. From 0 to T0, the response acceleration increases. From t0 to ts the response acceleration reaches maximum and remains constant. This zone is called maximum amplification plateau. After ts the response acceleration decreases. Generally, ASCE 7 to 10 introduces three types of response spectrum parameters to determine the design response spectrum (SA) of the structure. 1. Mapped maximum considered earthquake (MCER) spectral response acceleration parameters (SS and S1). 2. Maximum considered earthquake (MCER) spectral response acceleration parameters adjusted for site class effects, SMS and SM1. 3. Design earthquake spectral response acceleration parameters, SDS and SD1. We will study these response spectrum parameters as well as T0, TS, TL in the next parts. Now, we need to input the basic ground motion parameters. Ground accelerations are regional parameters. These parameters were recorded in previous earthquakes of considered locations. They represent the possible magnitude of earthquakes. Ground accelerations are often stored in terms of two parameters. They are short period acceleration, SS, corresponding to period t equals 0.2 seconds, and 1 second acceleration, S1, corresponding to period t equals 1 seconds. These values are represented in contour maps which are called seismic hazard maps. Next, we determine site coefficient factors. In ASCE 7, basic ground motion parameters from the database are converted to design spectral acceleration parameters, SDS and SD1, by site coefficient factors, FA and FV. Now, we need to calculate design spectral acceleration parameters. In ASCE 7, design spectral acceleration parameters, SDS and SD1, are taken as 2/3 of risk-targeted maximum considered earthquake, MCER, spectral response acceleration parameters, SMS and SM1. SMS and SM1 are calculated from basic ground motion parameters and site parameters. MCER are statistic basis parameters that are determined with a probability of 2% exceedance in 50 years. This is period coefficient. According to ASCE 7, period coefficient Cu is determined by design response spectra accelerations of 1 second, SD1. Period coefficient Cu is used to limit fundamental period, T, of structure. In this formula, Ta is approximate fundamental period. We will learn how to calculate it later. The next section is long period transition period. According to ASCE 7, TL is long period transition period. This is also a regional parameter, so it must be obtained from earthquake database. TL is used to calculate design response spectrum, SA, at any fundamental structure period, T, as following figure. It is noted that design response spectrum, SA, is calculated based on 1. Design spectral acceleration parameters, SDS and SD1. 2. Fundamental structure period, T. 3. TL, T0, TS. The start of maximum amplification plateau T0 and end of maximum amplification plateau TS are calculated from design spectral acceleration parameters, SDS and SD1, according to ASCE 7-10. After gathering all parameters, design response spectrum can be calculated as follows. Next, we will study about risk categories of structures. According to ASCE 7-10, the risk category is determined from structure characteristics. Category 1, buildings and other structures that represent a low risk to human life in the event of failure. Category 2, all buildings and other structures except those listed in risk categories 1, 3, and 4. Category 3, buildings and other structures, the failure of which could pose a substantial risk to human life. Buildings and other structures, not included in risk category 4, with potential to cause a substantial economic impact and/or mass disruption of day-to-day civilian life in the event of failure. Buildings and other structures not included in risk category 4, including, but not limited to, facilities that manufacture, process, handle, store, use, or dispose of such substances as hazardous fuels, hazardous chemicals, hazardous waste, or explosives, containing toxic or explosive substances where their quantity exceeds a threshold quantity established by the authority having jurisdiction and is sufficient to pose a threat to the public if released. Category 4. Buildings and other structures designated as essential facilities. Buildings and other structures, the failure of which could pose a substantial hazard to the community. Buildings and other structures, including, but not limited to, facilities that manufacture, process, handle, store, use, or dispose of such substances as hazardous fuels, hazardous chemicals, or hazardous waste, containing sufficient quantities of highly toxic substances where the quantity exceeds a threshold quantity established by the authority having jurisdiction to be dangerous to the public if released and is sufficient to pose a threat to the public if released. Buildings and other structures required to maintain the functionality of other risk category 4 structures. Next, we need to input the importance factor. According to ASCE 7-10, seismic importance factor can be determined from risk categories as follow. This part is approximate period. Now we will calculate the approximate period T, which has been mentioned in the period coefficients section. According to ASCE 7-10, the following empirical formula can be used to calculate the approximate period for all building. In this formula, is structure height, the vertical distance from the base to the highest level of the seismic force resisting system of the structure. Coefficients CT and X are determined as follow. Final coefficient is response modification factor. Response modification factor, R, accounts for the energy dissipation of building through ductility. This factor is systematically represented in ASCE 7-10. A part of the table is given below. This section allows users to input seismic load direction factors which are multiplied to seismic forces. Specify directions of accidental eccentricity forces. Select this option to include torsional moment due to accidental eccentricity. Click Add to save this load. Select considered floors. Click Seismic Load Profile to preview load configuration. Click OK to finish. Let's briefly summarize what we need to do to input seismic load according to ASCE 7 to 10. 1. Select desired standard. 2. Determine site class. 3. Find the basic ground motion parameters, SS and S1, from seismic hazard maps. 4. Determine site coefficient factors, FA and FV, according to basic ground motion parameters, SS and S1. 5. Calculate design spectral acceleration parameters, SDS and SD1, from site coefficient factors, FA and FV, and basic ground motion parameters, SS and S1. 6. Determine period coefficient Cu by design response spectra accelerations of 1 second period, SD1. 7. Determine long period transition period, TL, from earthquake database. 8. Determine risk category from functions and scales of structures. 9. Determine importance factor from risk category. 10. Calculate approximate period, TA, from structure properties. 11. Determine response modification factor, R, from structure types. This is the end of the lecture. Today we learn about inputting earthquake load based on the seismic map. Next week, I will show you a calculation example of seismic load.